Hello again, this is Brian. Before we get started on today's video, I want to talk about how you can grab the lecture notes for every video so you can follow along with the lecture on your own machine. You can download the notes from the link at the bottom of the video description with every single video, or you can visit the class GitHub at the top of the class website. GitHub is an online cloud storage provider for Git repositories. It's kind of like Google Drive for documents, but for code projects instead, Git repositories. And if you look through the folders and files within this notes repository, for every single week, we will post a new folder that contains the notes for the 2 lectures within that week. And inside this folder, you'll find the related code files, and you can open them up in this web-based code viewer just right here on GitHub if you just want to read the code. But what I recommend you do instead is actually download the code on your own computer so you can open it up in your editor of choice, usually that's IntelliJ, and make modifications to the code as you watch the lecture video. There's 2 ways to go about that. The simplest way is to click on this big green download code button and click on download zip. And what that's going to do is it's going to bundle up all the files currently in the repository into a zip file that you can download, unzip on your own machine, and then open up in your editor. The kind of annoying thing about this procedure though is that every single time I post a new set of notes, you're going to have to download zip again and then unzip and then open up. That gets pretty repetitive. So what I encourage you to do instead is once you start to learn Git, which I really encourage you to do, is to use a Git clone instead. And that way Git can automatically keep your repository up to date over time. So once you start to get Git installed on your machine, you should be able to run Git clone directly from your terminal. To do so, you can use this clone URL present in this code download window. Go ahead and use HTTPS for now. If you set up SSH keys, that'd be awesome, but that's kind of out of scope for this class. Use this link as the argument that you pass to git clone. So supposing Git is already installed on your machine, you can run git clone and then the link to the notes. And then when I run this, it's going to go to GitHub, download all the folders and files presently in the repository, and produce a cloned repository on your machine with the same folder name as the name of the repository. Then in the future, when I post new notes on the repository, you can enter that repository folder and then run a git pull to pull the latest notes. Let me demonstrate that now. So now I'm done cloning all the files. Let me clear my terminal so we can see everything. If I run dir or ls, or not lr, ls, we'll see that I now have a new CSC 143 notes folder. Let's go ahead and enter that folder using cd, CSC 143 notes. And now we see that we've got the folders and files for today's lecture and an archive of the old lecture notes if you'd like to see those. In the future, whenever I post new notes, you can then run git pull, git pull, and that's going to ask GitHub for any new changes that have been pushed to the repository that are not currently present on disk. Now that you have the notes, you can open it up in your editor of choice. Here's a neat trick on Windows to open this folder in Explorer. You can run explorer.exe and then the current folder. You can also, of course, navigate to this folder on your own computer in just Windows Explorer or Finder or whatever operating system file navigator you have. And then you can go into the folders for the day's notes and then open up the folder in your IDE of choice. Typically, this is going to be IntelliJ, but for this first lecture, it's relatively simple, so I opted to use VS Code instead. So you don't actually have to have IntelliJ installed at this point. Here's what it looks like in Notepad++. It's just pretty basic text editor. You can navigate around. You can modify this code for your liking, and you can also, of course, compile this on your own machine. Here's a simple Hello World program. Let's compile this by entering the folder cd 0405 intro Fibonacci git. Compile Java with javac hello.java. Which produces a hello.class, and then run the class with java hello. Hello world. Okay, that should be enough to get you started. Enjoy the video. Okay, so I've already got the notes pulled down, and I've opened them in my editor, Visual Studio Code. Now I've told you already that the recommended editor for this class is IntelliJ, but I'll show you a little bit of VS Code because Visual Studio Code is pretty minimalist and has very few requirements. That being said, its Java integration isn't nearly as strong as that of IntelliJ, but Fortunately, because our first lecture is relatively simple, I think it's an appropriate platform to present the basics. Let me go into presentation mode, and we can get started. Now let's talk about Java. As you probably know, Java is going to be this programming language in the class that we'll be doing everything with. Formally, Java is a compiled, strongly typed language. Let's break those ideas down, compiled and strongly typed. We'll talk about compilation first. Compiling Java is easy. I already told you how to install Java using that adopt OpenJDK installer, and that's going to give you the Java C and Java commands on your command line. Let's go ahead and pop open a terminal. I'll open my start menu, type CMD, open a command prompt. Then let me actually navigate to my folder where the notes are stored. That's cd into workspace /CSC 143, not grading, but notes. Do dir to look at the different kinds of folders I have in here. I need to cd into 0413. And this effectively puts my current working directory, that is the directory I'm currently examining, as my notes folder. Of course, you're going to have to navigate to the location of where you unzipped that notes folder, or where you did that git clone. So it's going to be based on where your downloads are. But in any case, once you navigate to the location of your folder, you can start interacting with the different kinds of files inside of it. So the first file I want you to take a look at is hello.java. This is a very basic hello world program in Java, which you should all recognize at this point. Let's go ahead and open hello.java. We've got our class hello. Of course, the class name in Java has to actually match the file name hello.java, so I've got a class hello. Then the entry point for all Java programs is this public static void main method. Main is just the conventional name for the entry point. A void is a function that has no return type, so this function is not going to return anything. A static method is a method that's attached to an instance of a class, but not, the opposite. A static method is a method that is attached to the class definition instead of an instance of a class, like an instance method would be. We'll learn more about instance methods in the future. And the public modifier tells other Java programs and packages that this class method can be accessed directly. Other modifiers, like private and protected, prevent other classes from being able to access certain methods and certain properties. We'll get into public, protected, and private later, but I do want you to know that this is going to be our entry point here, and this is going to be what runs when we actually run this program. We've got a single set of arguments, string args. String is the data type, args is the name of the variable as the argument, and it's an array type. So I can actually pass into main a series of strings in an array form as a single argument to the function. Typically, these are going to be whatever arguments you pass in to the Java program via command line. We're not going to be doing that at all in this class, but it is there in case you want to write a command line program. Anyway, that was a whole bunch of intro talk just to mention how we're going to do a system.out.println. System.out.println is going to print a string to the console. System and out. System is the top level library. Out is essentially a namespace within system. And system is actually globally available. So you might be surprised to see I don't have any special imports that indicate what system is or where it comes from. I can actually just call system.out.println without having to import anything. Here's my string literal, hello world, and my print line statement is going to output it to the console as well as append a new line to the very end. Okay, hopefully this should not all be news to you. If you come in with a Java background, this should all be very novice information, and I hope this is all review and catch up. If you don't come in with a Java background, I think you'll be mostly confused by some of the syntax here. That's okay. That's something you'll get over pretty quickly. As always, if there's ever any confusion about some of these special keywords that Java has, I do want you to be curious and ask questions about them. I understand that for a lot of you, this is going to be totally trivial, but I don't want this to be a point of confusion ever anytime we write software. I want us at the end of this class to essentially sort of be masters at Java. So even if you come with a Java background or don't come with a Java background, I do want you to know why certain things are written the way they are rather than just kind of accepting them as is. Anyway, this is our Hello World program. Let's go ahead and compile it by popping open our terminal and running Java C as well as Java. I'll go back to my command prompt. The dir command lists out the different kinds of files inside my directory. I see I have a couple files here. Let's go full screen. One of the files is hello.java. By the way, if you're on Mac or Linux, the equivalent command is ls, but unfortunately I'm on Windows here, so I don't get ls. In any case, let's go ahead and use that Java C program I installed, which we know is Java C version 11, to compile this hello.java program. And what Java C is going to do is it's going to take this Java, it's going to convert it into machine code that the Java virtual machine can understand, and it's going to enable me to use the Java runtime, which I had also installed alongside Java C. There we go, Java version 11, to run hello, where I can pass in the name of the class I'm trying to run, which has a main method, as the entry point for my Java program. There we go. Hello world. Nice. So not too much work. There's a couple of commands you have to remember, mostly just Java C and Java, but overall, getting started with Java is not too difficult. Let's go back to that README. So compiling stuff is just Java C and Java. Compiling Java is pretty easy for us Java developers. Now, compilation and execution is actually pretty hard for the Java language engineers. So what do I mean by that? Well, for us, we just have to know two commands. Maybe we have to know how to cd around to get around. Maybe we have to know how to write a little bit of Java. But the actual act of turning that code into something that runs on the computer is two very easy to run commands, Java C and Java. Now imagine you are a Java language engineer. You are someone who actually works on the Java language itself. And you are responsible for turning the literal text file that has system.out.println inside of it and turning that into something meaningful. If you think about it, the file itself, hello.java, just saying system.out, is totally meaningless. It's about the same as any other file that says anything in just plain text. It's really only meaningful because there is that Java compiler that knows what system is. It knows what out is. It knows what the literal string hello world means. And there's a certain meaning to all those different characters inside the text file. So if we want to convert it into an actual runnable program, we have to do a whole bunch of things. We start out by parsing the language. We examine keywords like public, static, void, main. We look at variables. We look at blocks like if statements and for loops. We have an understanding of what that language is and what it's trying to tell us. We compile it into something called a parse tree that essentially turns those expressions into a low-level machine language. We assemble that low-level machine language into JVM bytecode. This is essentially individual byte-sized instructions that will be understood by the JVM, the Java Virtual Machine. And then we have to execute it on a JVM that works in a variety of architectures like x86, ARM, MIPS, etc., etc. Maybe you haven't really heard of the JVM before. Maybe you have. The JVM is essentially the Java runtime, and Java bytecode is a special version of machine code that the JVM knows how to understand. And the clever thing about how Java works is because the JVM has been ported to virtually every architecture. x86 is the one that you run on your desktop machine. ARM is one that you might run on your tablet or maybe your mobile phone. All Android phones, for example, run a JVM to run their applications. We can essentially run any sort of Java program on any sort of computer architecture. This is not a computer architecture class, but we'll be talking actually quite a bit about architecture fundamentals. If you want to learn more about how different architectures work, I recommend you continue studying computer science and take an architecture course out of this one. In any case, I hope I've thoroughly confused you by all these steps because I want to emphasize this idea that compiling Java is hard, right? There's a lot of things that go on to make it possible for that simple hello world program to actually run on your machine. And it's pretty amazing that we can just go off to any store like Best Buy and buy a laptop and be able to run Java. And it doesn't matter who manufactured that laptop. It doesn't matter what operating system it runs. It probably runs Java, and I can probably run this one piece of file that I made on my computer. Okay, so again, a lot of complexity here. I don't expect you to remember it. I just kind of want to scare you into understanding that it's complicated, but also enjoying and appreciating the fact that it's easy for us to do via Java C and Java. This sort of conversion from complex to easy to understand is a kind of abstraction. This is a big keyword in this class, abstraction. Abstraction is about masking the complexity of something, of a system, with simple interfaces. Let me give you some real-world examples that you will probably recognize. A grocery store sells meat and vegetables, which require pastures, farms, tractors, and processing plants. But I can still go to the grocery store with no knowledge of how to operate a farm, how to operate a tractor, I can go buy 4 pounds of ground beef for a relatively cheap price and have zero understanding of the process that took that cow and turned it into ground beef. Similarly, compilation is a complicated process. Compilation is kind of like that farming or running that tractor, but all we as Java developers have to do is run javac, and we get that entire compilation process with one command. So my point here is, the grocery store abstracts away all this hard work and labor that has to go on and gives me a very simple interface. I just have to go into the store, pick up the items I want, and go through checkout. Compilation is the same way. It abstracts away all the complexity of language design and language understanding, and I get this very simple interface, javac, the name of my file. Formally, an interface is a set of interactions made available by a system. So a grocery store accepts money for payment instead of labor like raising chickens. The interface for javac and Java, well, Java takes a minimum of 1 argument, a file to be compiled. I'm not sure what these little characters in my file are. Java takes a minimum of 1 argument class to be executed. Abstraction and interfaces go hand in hand and are going to be a recurring theme for this class. Okay, now let's talk about the second part of that Java definition. Strong typing. What does it mean to say that Java is a strongly typed language? In Java, every variable has a type, and the validity of the type is strongly enforced. So let's take a look at some examples. I'll open a file called types.java, and I'll get a whole bunch of different types definitions in my main method here. Let me start out with some very simple class definitions. We'll get into classes in more detail, but the simple introduction is that a class is sort of like a blueprint for an object. It can store different kinds of data fields. Perhaps the simplest definition of a class is one that just has data fields inside. So here I have a class A, it stores an integer x. Then I have a class B that extends A, and it stores a single integer y. This extends keyword is something we'll go into more depth in into a couple weeks, but for now what you essentially need to know is that B is a kind of A that inherits all of A's properties. So B is not only just going to have an int y, it's also going to have an int x. You just don't see the int x in B's definition. B just gets everything that A already has. Now let's take a look at our main method. Java has quite a few set of primitive types, so they're called. Primitive types are indicated by how there are not capital letters at the front of the type definition. We've got some pretty basic ones like char for a character, which stores a single letter, int, which is just a number, an integer, a boolean, which is true or false, and double, which is a floating point value. It's a decimal integer. Well, not an integer anymore, I suppose. It's just a decimal value. A long is a kind of integer that's wide. What does that mean? So an integer in Java takes up, by default, 32 bits. That is 8 times 4, a total of 4 bytes. A long is like an integer that's twice as wide. It's actually 64 bits. And what that gives us is it gives us more space to represent numbers. In a long, by nature of it having 64 bits, I'm able to express numbers that are much greater or much smaller than what I can just express in the space of integers. We'll maybe talk about bits and integers in more detail later, but long is one of those types that are kind of good to know in case you need to store integers that are pretty large. Now what happens if I try to assign my long to my double? Remember, my double is a decimal type. My long is just a very wide integer. Let me go ahead and try compiling this and see what happens. javac, and the file name is types.java. Oops, I get a compilation error. I'm told types.java at line 17, which is going to be this line, expected a semicolon. I see. I forgot to comment out not okay. Let me fix that first and then compile again. Okay, here's the error I actually want to see, which is at line 17, I get incompatible types, possible lossy conversion from double to long. What it's telling me is that my double is going to be coerced into this long if I try to do this, and it's actually going to stop me from doing that. It's an error. This actually prevents me from actually running my program. It's not going to generate an executable when I compile types.java because it says, no, this is not okay. This is like trying to put square peg into a round hole. I'm not going to let you do it. So this is one kind of nice thing about Java, right? If we have different kinds of types and we have a really big program and a lot of things going on, it's going to stop me in advance from making this type of mistake. If there's a lot of things going on in my program, I have a lot of different mixed types, it's entirely possible that I just get confused, I write some lines of code down, and I try running my program, and mistakes are made, right? So here, by being told in advance during the compilation step, I can save myself the headache later of running my program and then hitting this error during runtime. Let's take a look at some other examples. A float is essentially a half precision double. The reason doubles are called doubles is because they're 64 bits, but a float is a 32-bit decimal type. We typically don't want to use floats because they're not very precise. You'll learn more about how floats are stored when you take an architecture class, but I suppose what you need to know now is that 32 bits is not really enough space to store decimal types with very much precision. This is just the nature of how binary decimal types are stored, and if you try to store a number in a float, chances are it has to be rounded to a different number. That's not what you expect. There is such thing as a decimal literal, but here you can actually cast it into a float. This, by the way, is the syntax for casting. So if this is a double on the right-hand side, I can put the type that I want it to actually be, and then surround it with parentheses to cast it to a particular type. Now, this kind of casting is not always legitimate, but here, because a double and a float are kind of the same family, it's something I can do. Java is also going to permit me to put my float inside my double. By nature of my float being the smaller type and my double being the wider type, I can in fact fit whatever decimal number I'm representing in my float into the space of what I'm representing in my double. Let's take a look at some other invalid conversions, like my attempt to cast this Boolean literal false into an integer. Integer is of course a number type. A Boolean is of course true or false. I'm not allowed to do this if I try to compile. Let's see what happens. Java C, types.java. I am told Boolean cannot be converted to int. Right, not good. So I'm not allowed to do that. What about some of these math operations, like 5 plus 5.0? 5 on the left-hand side here is an integer. 5.0 is a decimal type. And Java's actually going to let me do that. It's okay. I'm allowed to add an int plus a double, and it's actually going to give me a double back. So that's all right. The point here is that you can actually take different kinds of types, like numbers, and use operators to essentially convert them into other types. So here I've got a 5 on the left of this greater than sign, and a 0 on the right. And this greater than sign operator is going to give me a Boolean on the way out. So you can kind of think of the operator itself as a function between two integers, those unique types, and returning a type of Boolean. Similarly, functions work in the same way. Here are two function definitions. The first one is public static Boolean is even. It's just going to ask whether or not something is an even number, and it's going to return true or false depending on that outcome. I can use the modulo operator to get the remainder of the value after it's been divided by the number on the right-hand side. So this is essentially asking, is the number divisible by 2? If so, it should have a remainder of 0, and in that case, return true. Otherwise, return false. This is going to work, but it's actually a little bit more verbose than it needs to be. And remember that I can use certain operators to convert types into other types. So here, I'm essentially using the modulo operator to turn a number and a number into another integer, and this double equals operator, which is the equality operator, to convert two numbers into a Boolean. And given that this expression itself is a Boolean, I can actually just return that on its own. Here's my isOdd function. It's much shorter. All it does is return the outcome, the Boolean outcome, of whether or not the number is divisible by 2. If it's not divisible by 2, then of course we know it's odd. Otherwise, if it is divisible by 2, then we know it's even. Anyway, back up here, I can call these functions isEven, isOdd by passing these integers in and getting Booleans on the way out, because that is the defined return type for these functions. These functions take integers and then return Booleans. A couple other things here. I've got a string. This is a string literal, hello world. like we saw in the hello world example. Here I'm trying to cast that string into an integer. Take a look at these type definitions carefully. One thing you'll notice is that they start with a capital letter. Type definitions that start with capital letters by convention are types that are not primitive types. These are considered object types. An object is essentially an instance of a class. We'll talk about classes in a lot more depth, and if you have a Java background, again, these class definitions should be reviewed to you. But if you don't really have a Java background, that's okay. What you essentially need to know is that by nature of these classes being able to have fields and have functions and other things attached, they can be much more complex than the just simple bitwise primitive types. So this string here, hello world, actually has interesting methods attached, like length, toString, I guess toString's not that interesting, hash code, and stuff like that. Same thing goes with the integer. Integer has a toString. Integer has other methods attached to it. And by nature of it being an object type, it's actually quite a bit more complicated than these basic primitive types. So what happens if we actually try to cast a non-primitive type, an object type, into another object type? Well, if I try to pass this message, the literal string, into an integer via casting, I get that error that I already saw during compilation, which is string cannot be converted into an integer. Not good, right? So that's nice. Java's going to stop me from making that mistake. But now let's see what happens when we try to use something in a class hierarchy. Remember that A and B class that is defined at the top of the file? I have class A, just has an int x inside, and class B that extends A, which has an int y inside, in addition to whatever A gave it. If I declare a new A and declare a new B, I can actually assign the reference to my B into my A. So that's kind of interesting to think about, right? B is its own type. It's got more data fields than A does, but B's are A's by nature of B's extending A's. One way to think about this is that B fulfills all the expectations that A's fulfill. If you're ever asking someone for an instance of A, if they give you B's, that's okay because B's do everything that A's do. B's have all the fields and all the methods and all the functions that A's have. So I'm allowed to put an instance of reference to a B in the space where an A belongs. Now what happens if I try to put an A into a B? Is that okay? Well, let's go ahead and try compiling our file first and seeing what Java tells us. Let's go ahead and comment out that invalid object typecast. And it does compile. It does compile. In these previous examples, we saw how a lot of these invalid type conversions, in fact, all of these invalid type conversions, prevented the program from compiling. But here, it seems as if I'm allowed to put A's where B's belong, even though A is actually the parent of B. So is that okay? What happens if I try running my program? Oops. I get an exception, a Java lang class cast exception, which tells me class type A cannot be cast to a class type B. Type A and type B are not going to be compatible. So what happened here, right? All these primitive types, every time I tried to convert something into something that wasn't okay to be converted to, I got a compilation error. But here, I get a runtime error. Let me say that again. Up here, anytime I tried to make one of these invalid type conversions, the Java compiler stopped me from doing it. I was told in advance, before I even ran my program, that I was doing something that was not okay. I was trying to fit a square peg into a round hole. But down here, in this example, I was able to compile okay. I was able to get my program into an executable state. But the moment I ran my program, the program crashed. I got that exception. So what's the big difference? The big difference is that Java doesn't know in advance, among a hierarchy of types, what references what and what is okay to put inside another reference. Remember up here that I wasn't allowed to put integer and string together. I wasn't allowed to put the string into the integer. And that was because string and integer are two different classes that live in two different hierarchies. Neither inherits the other. But here, B's inherit from A, therefore all B's are A's, and I can put B's wherever A's belong. But down here, when I try to coerce an A into being a B, well, I'm not allowed to do that anymore at runtime. But Java also won't stop me from doing it at compile time. Why is that the case? Why is that Java is kind of stupid here and doesn't stop me from making this happen? Well, consider this example. Suppose I give you an array of A's. I give you a whole bunch of instances of A. Now, I told you that all B's are A's. I can actually put B's where A's belong, and that's okay. So in the case that some of those A's are actually B's, it would be okay for you to receive all those A's. Again, I give you several A's, and some of them are B's. But that's fine, because all B's are A's. So I can give you a series of A's that are either A's or B's. Now, let's suppose you try to give me a series of B's. You try to give me all those A's back that I gave you originally. Well, some of them are indeed B's, so that's okay, but a lot of them are actually just A's, and not all A's are B's here. So in this case, I can't necessarily accept the B's that you're offering me if some of them are actually A's underneath. And here the deal with Java is that Java has to permit the direction in both directions, the assignment, because Java doesn't know in advance what the type you're going to be giving me is. Even though it may seem obvious from the code here, if this is part of a function that returns types of B's or types of A's, the type on the right-hand side may be ambiguous to the program. There may be so many different layers of typing going on, and so many different types of typecasting going on, that Java can't possibly know during compilation time whether or not A's or B's are being received on the right-hand side. So Java's just going to let me do it, but it's also going to crash the program when it happens. Again, this is because I'm allowed to make B's be A's, but I'm not allowed to make A's be B's. However, there are circumstances where it's ambiguous what something is, and Java's going to give me the benefit of the doubt and let me make it happen. In the previous example, it wasn't ambiguous that these types couldn't be combined because they lived in a different hierarchy. Under no circumstance can a string be an integer or an integer be a string because neither is a parent of another. But here, A's are the parents of B's, so all B's can be A's. But if I have a whole ocean of A's, some of them might actually be B's, and therefore some of them could be permitted to be assigned to a B reference. So, strong typing. It is strong for the most part, but it's not foolproof. That's what I want to emphasize here, is that for the most part, for these primitive types and for these classes that are of mixed hierarchy, I do get that nice abstraction of strong typing. I'm told when I'm going to make a mistake during runtime, but instead I'm being told at compile time. Here though, here's an example where I have two classes within the same hierarchy, and it's ambiguous to Java at runtime what a certain type is. It has to figure it out when it's running. It can't know at compile time. So I'm not actually stopped during compilation. Instead, I'm stopped during runtime. Now, being stopped during runtime is actually much worse than being stopped at compile time. Let's take a look at the README. Being stopped at compile time is essentially being told, you can't ship this. You are writing a program that is not valid. If you run it on people's computers, it will crash. So imagine you are some sort of software engineer contractor, right? And you're tasked with fulfilling a certain set of specifications. If the compiler tells you you're making a mistake, it's saving you from the hassle of giving your contract, or giving the person who signed the contract with you a program that's broken, right? If the compiler didn't stop you, you would be giving that person, whoever you're serving, a program that is broken. But fortunately, the compiler does stop you. So it's going to stop you in advance from making certain mistakes. But the compiler won't stop you from making all mistakes. And that example that I just showed you with A's and B's is an example of an error that can only be determined at runtime. Those runtime errors are not so good. This is the equivalent of you giving whoever you contracted with a program that runs, but then eventually crashes. You would much rather have that program crash on your own machine during development than crash on their machine. Let's think of some real-world examples. Let's suppose we were writing an ATM software, and we were developing the software for the ATM panel, where you go into the ATM and you start punching your PIN code, you put in your debit card and stuff like that. If you were an engineer working on the ATM, and you receive compilation errors, that's good because it's on your own computer. You can still work on it, you can fix those errors before you ship it out to people. If you didn't have compilation errors and you shipped out a piece of software that was deployed to all those ATMs, but there were errors at runtime, then people using those ATMs all around the world would have trouble accessing the money because maybe the ATM software crashes. So we want that compilation step. We want it to tell us when we're making mistakes. But the pitfall is that it can't make all the mistakes. It can't determine all the mistakes for us. So we need to be careful as developers to know when Java can save us from making errors and cannot save us from making errors. And we need to be very conscious about the distinction there. But we do like the compiler in that case. We always want to see a compilation error in favor of a runtime error. So we know in advance before we sell our product that mistakes are being made and we can resolve them. So in summary, you can't assign a variable to an incompatible type. That is, primitive types can't be mixed, and object types that are of different hierarchies can't be mixed either. You can't pass a variable to an incompatible argument. You can't class an object to an incompatible object. You can transition from one primitive type to another type using operators, such as that greater than operator or the Boolean operator, that is the modulo operator, that returns numbers converted into Booleans. Java is going to prevent us from making a lot of those type errors, but some type errors can only be detected at compile time, and others can only be detected at runtime, which is bad. Now I'd like to talk about something that relates more to the practical side of writing programs, and we're going to do it in the context of writing a Fibonacci program in Java, similar to the one that we wrote at the beginning of the class in Python. To put this in context, I want to bring up some practical issues that you might overcome when just writing software. The first is that, well, programming is complicated. A lot of code depends on other pieces of code. Whenever you use the Java standard library, you are trusting that the standard library code is going to perform correctly, and that whatever version of the library you're using isn't going to cause maybe substantial changes in the programming interface or the behavior as you update those dependencies. In the worst case scenario, one small change can easily break everything. And if you make that one small change, or someone else makes that small change for you, it can be hard to recover a working copy after overwriting all your existing files. Having your programs be just fixed to a specific file or set of files essentially creates a single source of truth. It's whatever is currently on disk. And if you're going to only have a single source of truth, it's going to prohibit you from doing large-scale experimentation. If you want to rewrite your program or take a different path when it comes to your program's architecture, that poses the risk of overwriting the existing working copy that your program is already in. And having a single source of truth means you can only really step in one direction, but it's kind of hard to come back. Again, it's hard to recover the working copy after you've overwritten the file. Finally, someone else can clobber your code by overwriting it. If you're working on a shared piece of software where you have several different collaborators, and maybe you have your code stored on a single central server somewhere, if somebody else comes in and changes it and overwrites it, they might end up destroying this one working copy that you have. And of course, that's a very frustrating experience. So version control is a kind of software that's meant to alleviate us from all these different practical problems. And version control is software that tracks code changes over time, enabling us to follow different versions of our code as it is developed. Let's go take a look at that Fibonacci file and develop different versions of that Fibonacci program and use version control to enable us to go forward and backwards in time with the reassurance that we will never lose our working copy of that program. Okay, so here I've got a very basic shell for my Fibonacci program. I've got a public static void main. All it does is call the compute range function, which in turn calls compute recursive, which as you can imagine is going to get me the nth Fibonacci number, and compute range is just going to do it from the range of 0 to the index maximum that I've specified in the argument. Arrays.toString is just going to convert that array output into a string, and system.out.println is going to, of course, put it to the console. Let's go ahead and compile it as is to see what happens, just so we can have some context. Okay, and when we run it, we get 10 numbers that are all 0, which is as expected because I asked for the first 10 numbers of Fibonacci, it called compute recursive, and I always return 0 every single time. Let's go ahead and write in that basic recursive implementation. With the recursion version, all I had to do was set up some base cases and then recursively call compute recursive whenever I had an argument that didn't quite match my base cases. Of course, our base cases are going to be when n is 0 and n is 1, the first two numbers of the Fibonacci sequence. Perfect, we've got our base cases down. Now in the scenario when n is greater than 1, we need to think about what we're going to return as the output for that nth Fibonacci number. Of course, we know that Fibonacci numbers are the sum of their two predecessors, so we can do the sum of compute range of n minus 1 plus compute range of n minus 2. Great. There's maybe a couple other things we might want to add here, like checking for preconditions, maybe throwing an exception if n is negative or some number out of bounds. But as far as the most basic requirements for a recursive program goes, I think this goes ahead and fits that. Let's go ahead and compile it and run it and see what happens. Whoops, bad operand types for binary operator plus, compute range, n minus 1. Instead of calling compute range, or instead of calling compute recursive, I instead called compute range. That's very nice that the Java compiler warned me of this type error. In compute range, I'm getting integer arrays. In compute recursive, I'm getting the integers, the nth number of the Fibonacci sequence. Of course, I want compute recursive and not the other one. Compile and run. Great. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. That sounds about right to me. Okay, awesome. So now that I've gone from my empty shell to having a working Fibonacci program, I want to turn to using version control to save a snapshot of this working environment so that if I choose to start to experiment with other implementations, I can still come back to this one as a reference and just to have a working copy on hand. Let's go back to the README for some instructions and guidance. Okay, so while we're writing our program, let's think about what the kinds of things we want in a version control system. We want it to be easy to take snapshots of our current code base. We want to be able to save the current version of Fibonacci so that I can come back to it later. I want it to be easy to branch the existing code and track several versions at once. Maybe I'd like to rewrite my Fibonacci program in an iterative fashion, but I also want to come back to my recursive version as a reference easily and maybe decide after I finish both which one I'd like to keep. I'd want for it to be easy to collaborate with others and allow others to make changes without interference. This goes back to that somebody else can clobber your code example, where if you're working on a shared project and you only have one file system that's the source of truth, it's very easy for someone else to overwrite your program. We like version control to let us all work together at once, but also make it possible to delineate what parts and what contributions are given by others and how to merge those together with our own. Lastly, we do want it to be easy on the file system. We don't want it to take a naive approach of just copying and pasting our files every time we make a new version. That means every time we make a change, we have to consume the same amount of space we've already consumed for the file. That really doesn't scale up, especially for these larger projects. Now let me tell you about Git, spelled G-I-T. Git is a popular command line version control software used throughout the industry for its relative simplicity and efficiency. I use Git at work. I've used Git at just about every software engineering job I've ever worked for. I really recommend it as something you pick up as early as possible so then you can use it throughout the rest of your academic and professional career. Some definitions about Git. A repository is where all the code for a program is stored. This is just a fancy word for the root folder. Commits are these individual changes that you will tag with a message. So every time you update your program, maybe just a little bit or a lot, you can make a commit and say, I added XYZ or changed XYZ. Branches are different independent variations of your program. Maybe I'll have my recursive version of Fibonacci. Maybe I'll have my iterative version of Fibonacci. I can create separate branches to track the development of those two versions independently. Your final program is going to be the sum of all your commits together. I've put this download link git-scm.com on the class webpage where you can go install Git on your own machine. It's kind of like installing Java. I'd like you to verify that it's installed locally by opening up a terminal and running git-version. That should give you the latest Git version. Let's go ahead and try it now. Looks like I'm on 2.7.4. The version number isn't really that much of a big deal, as with Java, as it is with Java, where in Java every version change is going to cause significant differences in implementation and available interfaces. Whereas in Git, generally the upgrades are rather minor and most versions are compatible with each other. Whatever you download from Git SCM should be the latest version. Now let's talk about how you actually use Git. We'll start out with the most basic step, which is git init. And this is going to initialize the repository once inside the root folder. For the class notes, I've already done a git init, so I won't do it again. But if this were the beginning of your project, I would really recommend doing a git init at the root of that project folder. What it's going to do is generate this .git folder. Well, I suppose you can run it twice. It'll just reinitialize. dir, remember that's the command to print out files in the folder. ls is the equivalent for Linux and Mac. There's two arguments you can pass to ls, which is a, which is going to include all files, hidden files included, and l, which is going to do it in list format. Anyway, I'm telling you this because when you do the git init, it's going to generate inside that root folder a .git folder. And this one .git folder is going to store all the information Git needs to track your program and stage commits and save commits. What's nice about that is you know that everything Git needs to keep track of your program is in one place. It's not going to attach additional metadata to all your files. It's not going to make changes to any of your files. It's really only going to store everything it needs to know inside this one folder. Once you've done that git init, it's time to do a git status. And when you do git status, you're going to be told a lot of things. You're going to be told which branch you're on. Master tends to be the default branch. You're going to be told what changes are available. Here it tells me I've actually modified Fibonacci since I last committed. And it also tells me what kind of changes I have currently staged. We'll talk about the staging area later, but I think we'd better focus on what we've made in the changes for our repository so far. So it's telling me I've modified Fibonacci.java. And it's telling me this because I've made changes to Fibonacci and I have yet committed those changes. I haven't attached description to those changes. You can use the git diff command to print out in the console a nice looking version of all the interesting changes that have been made in the current state of the repository. Let's do that now, git diff. And if we use the arrow keys to go up and down, we see that, well, we started out with compute recursive and we got rid of the return 0 and instead replaced it with our recursive implementation. So git diff is telling us, since we last committed, I made these following changes. I had gotten rid of the old code and I'd implemented it with our new code here. Let's do git status again to bring us back to the status info. Now let's go ahead and make a commit. In order to do that, I'm actually going to have to stage my changes first. This is like kind of putting your current changes into a place that are going to be shipped off to form a single commit. Let's go ahead and add that Fibonacci file. I'll do it with git add, pointing to the directory 0413 Fibonacci.java. When I do a git status again, I'm told that file is now staged for change. And now when I do a git commit, what's going to happen is it's going to take whatever is currently staged and save it as a commit. Git commit takes a single argument, well, two arguments actually. Well, actually several arguments, but the ones that I think you'll be using the most are the -m, which indicates you're going to be passing a message, and whatever message you're going to be putting in double quotes here as a string. So here I'll say implemented recursive Fibonacci. I'll do git status one more time, and now I'm told that there are no new changes. The working directory is clean. What Git's telling me is that since I just made a commit, the latest version of the repository has all the latest changes. the version that I'm being shown in my code editor and on disk reflects the code that was saved inside Git. Okay, now that our Git repository is all up to date, let's go ahead and try making some changes, making some experiments, and seeing what we can do with this power of version control. All right, so I told you at the beginning of class that this compute recursive function here is actually quite dangerous. If I pass in a number, n, that's something very large, like 5,000, it'll actually take more than the lifespan of ourselves and of the greater universe to actually finish computing. To prove it to you, let's actually try running it on our computers. Let me go ahead and replace this compute range from 10 to 5,000, the number I showed you in the presentation, compile it, and see what happens. Whoops. Git status tells me I've made a change to my file. Git diff tells me I've changed that 10 to 5,000. Okay, sounds right. Let's do a Java C, Fibonacci.java. Actually, I'm in the wrong folder. CD 413, Java C, Fibonacci.java, Java, Fibonacci. It's going. It's going. My computer fan is starting to spin up. And we could wait here all day and it would never finish. To further drive this point home, one thing we can do is insert a print statement between each computation, just to let us know how the progress is coming. That way, every time it computes a new number, we'll get an output in the console. Git diff tells us that we added that print statement. Let's do a Java C of Fibonacci.java, Java Fibonacci, and let's see what we get. Okay, so we got like the first maybe 40 or so numbers down pretty quickly. And then it takes increasingly longer for every number after that to come out. As you can imagine, it takes actually about double the amount of time as the previous number. And although that amount of time difference, that time delta between numbers starts really small, it really does grow and grow over time to the point where we're not even close to reaching 5,000 and it's ground to a halt. Yeah, this is not going to finish anytime soon. If you're in your console, by the way, press Ctrl-C to quit out the program. I do want to point out something quite interesting though. This negative number here. Now, it's kind of coincidentally the last number that printed out before I quit the program, but this is something to keep in mind here, this negative number output. Why is that possible? Well, even though our Fibonacci implementation only ever adds things together, and we only ever get non-negative numbers here, you can actually only store so many numbers. Let me rephrase. You can actually only store numbers that are so large inside of an integer. Remember about 20 minutes ago, I taught you about the primitive types and like how long is a version that's longer than int. And I can store numbers that are larger inside the long because it takes up 8 bytes rather than the integer, which takes up 4 bytes. What's actually happened here is an outcome of integer overflow. I've added together some numbers that are so large, I physically can't fit it inside the integer. And what I've accidentally done is flipped a bit inside that integer that tells the integer that the counting should start from negative rather than positive. The outcome of that is I get these negative numbers on the way out. Doesn't make a lot of sense from a, I suppose, fundamental point of view, but from a practical side, this is something that we're going to have to run into and we're going to have to deal with when we actually write these programs that deal with these very large numbers. We're going to need some more bit space to represent bigger numbers that would otherwise not fit inside our basic int. As a very basic upgrade, you may consider refactoring this code to use long rather than int, and it may last you a little while longer. But also remember that Fibonacci grows extremely fast. We started out with very, very little. We started out with numbers that were very, very small, and we introduced a new digit to our Fibonacci sequence basically every couple of numbers or so. So even if we replace this with long, which gives us twice the precision, and gives us several more numbers we can use. Eventually, we're going to hit this limit again, and eventually we're going to reach that negative number. We'll talk about how we're going to deal with this soon, but right now let's focus on actually fixing this runtime problem where it's super slow, and think about this integer overflowing problem in a later section. Okay, let me go ahead and get rid of these changes. One nice thing about VS Code is that you can actually get inline Git integration. So it's actually telling me in line that I've made these changes to my file. It's really cool and lets you quickly revert back if you need to. IntelliJ is going to let you do this too. I'm going to go ahead and use the GUI to do it, to demonstrate how we can get back to our repository as it was when we just committed. Git status tells me we have no changes. Git diff is empty. Nice. Okay, so when I told you about version control, I promised you how we could very easily take branches, experiment, without ever risking our existing working copy of our program. Let's go ahead and do that. Let's go ahead and destroy our recursive implementation because we know it's kind of broken in terms of runtime, and write an iterative implementation instead. Let's think about that recursive implementation. We had 2 function calls for every time we called the function, and it grew exponentially because this was by nature recursive. To calculate Fibonacci sub n, I had to go find out n-1 and n-2, each of which also found out which of its predecessors were, and so forth, until we finally reach this base case. The nature of the Fibonacci sequence being very predictable, though, means that we don't necessarily have to do it in this recursive form. It may be naturally a recursive definition, but we can also build it up in a slightly different way. What I mean by that is, consider these base cases one more time. If n is 0, return 0. If n is 1, return 1. Well, what if n is 2? If we do it by hand, 0 plus 1, it's obviously not sustainable for us to go about defining n for every single n in existence, but we are programmers. We can do better. We can write a loop structure to do this sort of repeated iteration for us. Well, what do I mean by that? If n is now 2, or some number greater than 2, I can start computing Fibonacci sub I until I reaches the nth number I want to reach, and just have I be the sum of the last 2 numbers that I've already generated. If I already know my base case, the first number and the second number, then I can generate the number that comes after that. And then I can use that new number that I just figured out to generate the number after that, and so forth. Let's go ahead and do this. Let's have an int before, or actually let's call it int first. We'll make it our base case of 0, fib sub 0, and second be 1, our base case when n is 1. And now that we've reached fib sub 2, we're going to make this new number that we're generating be the sum of those 2 previous numbers. Let's call that next and save it in that variable. Okay, let's go ahead and keep computing next inside the body of this loop. And now that we know next, we can shift our 2 predecessor numbers forwards, since we're going to go ahead and compute the next number after this. What I mean by that is fib sub 3 is now going to be the sum of second and next. So let's go ahead and replace first with second and second with next. Nice. Now what this is going to get us is the iterative computation of Fibonacci. I start out with these base cases, and over time I'm going to compute the next number, and using the new information I've generated from that, the next number after that, and so forth. There are no recursive calls here. And the great thing about it is I'm really only counting from 0 all the way up to n. Rather than the previous 2 to the n version, this is actually only a big O of n implementation. We call that linear time. When we're done, of course, we have to return our final value, which is going to be next. Great. I've taken what was a program that grew exponentially to a program that grew linearly. Yes, the greater the n, the longer it will take, but I'm not going to hit that problem where we face the Hydra, where every time we solve one of these recursive calls, we have to solve 2 more. Instead, every time I solve a number, I just move on to the next one. Okay, let's go ahead and rename compute recursive because it's no longer appropriate. Let's just call it Fibonacci. Compile it and see what happens. Okay, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. Awesome. Those are the numbers that we got out of that recursive version. Let's do a git status. We're told that Fibonacci has changed. Let's go ahead and do a git diff. We see that we trashed our recursive version and we replaced it with our iterative version. Okay, before I go ahead and commit these changes, let's actually go ahead and branch out. Remember, branching is cheap. And I'll show you the command for creating a new branch. When we do git status, we're told that we're currently on the branch master. One other way to get to that is to write git branch, and it'll put a star next to the branch you're currently on. Now to check out a new branch, that is to say to branch off or fork off the existing branch, use the command git checkout -b. And the argument you pass in after that is your branch name. Let's call it iterative. Now I'm told I've switched to a new branch iterative. If I do git status one more time, I'm now on iterative and not on master. So the nice thing about being on a separate branch from master is that I can make commits to this branch and they don't interact with commits on the master branch. Let's go ahead and add that Fibonacci file and then commit with a name, commit-m. Let's give it a message like replace recursion with iteration. Great. Now that I've made that commit, my git status should tell me I've made no changes. Okay, now let's do something fun. Let's raise this number from 10 up to 5,000 again and see what happens. Hopefully it finishes this time. Let's check it out. Java C, Fibonacci.java to compile the program, and Java Fibonacci to run it. Awesome. It actually finished. Look at that. It's beautiful to see, except for the fact that we're getting all those negative numbers. We start out with our introductory sequence that we all know and recognize. Then after a certain point, it hits negative numbers. It starts flipping back and forth because of all the integer overflow. So not perfect, but we did make a lot of progress here. By converting our recursive 2 to the n function into a linear iterative function, we were able to actually compute all those numbers on a local computer within a fraction of a second. That is pretty amazing. And this is going to be a pretty big theme throughout this class, is how we make decisions around our implementation in terms of the kinds of trade-offs that we're going to be making. In that recursive solution, we got a very simple implementation. In fact, it was actually quite elegant. I would argue that that is the most basic implementation of Fibonacci you could write by nature of how the sequence is defined. Here we have a bit more complexity. We do have to store a little bit of state. We have to remember the last 2 numbers we computed. But what it gives us is something that runs so much faster. This is actually usable in terms of our lifespans. And even though they're solving the same problem, these 2 different approaches have 2 vastly different runtime costs. Let's do a git status and a git diff. All I see is that I've changed 10 to 5,000. Let's go ahead and commit it anyway. And now we're in a clean state. All right, now let's suppose, now that I'm done with this iterative implementation, I like to go check out my recursive implementation one more time. With version control, I can very easily switch between the different states of my program without ever losing access to any of them. The git branch command is going to list out the kinds of branches you currently have. Remember, I had master to start with, and now I'm on iterative because I checked out a new branch and started committing. If I git checkout master, which is the name of the original branch I was on, and I don't pass in that -b flag, which is used to create a new branch, what's going to happen is that Git is going to take me back in time to the version of my implementation that was actually recursive. This is because the last time I committed on the master branch, I committed this recursive version. The last time I committed on that iterative branch, I had committed that iterative version. So if I go git checkout, iterative, I'm taken forward in time, my files are updated, and I get my iterative version back. The really powerful thing about this system is that there's never any risk to go out of your way to try something new. Maybe this iterative version didn't quite work out. Maybe we got ourselves in a really bad state, our code stopped compiling, and we wanted to just give up. Thanks to version control, I'm able to go back in time to my working copy of my code, no matter how bad my current state is. That's really, really nice. It's such a great reassurance to have whenever you're working on software that is very complex. Okay, now we're almost done, but we're not quite done. We still hit this negative number problem. I'd like to get around that by doing something that's going to give me numbers that have larger precision. I've told you already how the long is twice as wide as the int, and I can store many more numbers in the long. But if you actually go ahead and try converting all these ints to longs, something maybe you can try on your own time, you'll find that eventually it's still going to hit that integer overflow problem, because the long is a fixed width. Even though it's wider, we can only store so many numbers inside 8 bytes. I'd like to introduce you to the BigInteger as a way of getting around this problem of integer overflow. BigInteger is a class in the Java standard library that is going to let us have unlimited precision ints. What do I mean by that? Well, integer was 4 bytes. I can only store numbers that were so large. Long is 8 bytes. I can store more numbers, but still, there's a limit to that. What if we had an integer that would just keep growing and growing and growing, consuming more bytes whenever we needed them? That is the BigInteger class. And that is perhaps the very first piece of abstraction that we're going to be using from the Java standard library in this class. Let's go back to our implementation and convert our implementation here into BigInteger equivalents. Instead of returning an int, let's return a BigInteger. And maybe instead of taking an n argument, let's take a BigInteger in. So even without knowing how to use the BigInteger, just knowing about it, I can kind of deduce some of the things I can work with. By nature of it being an integer, it better have some comparison methods. So if we try something like if n double equals 0, hopefully that will work. But what you'll quickly learn in Java is that when it comes to object types, remember an object type is a class that starts with by nature, or by convention, starts with a capital letter. All object types are going to have a method called equals. And we're going to use equals to judge whether or not our big integer n is equal to another big integer. The reason we don't usually use these primitive operators is that generally these are reserved for primitive types. There are some exceptions to this rule. I think BigInteger might actually be one of those, but because we're learning about object types, I'd prefer we go ahead and use these object type methods. A method is a function that's attached to an instance of a class. I can invoke methods by using the dot operator on the right of a reference to an object, and then calling that method name with the arguments required of me. I know from experience that BigInteger.0, capital 0, is a property of BigInteger that just returns a static value integer that is equal to BigInteger of 0. So what I'm simply asking here is n equal to BigInteger 0? If so, let's go ahead and return 0. It's our base case. Because we're using these non-primitive types, these object types, we do have to work a little bit within this special system of the BigInteger rather than these simple primitive types that we've learned. Just like with this conditional statement using BigInteger.0 to represent the 0 int, I'm also going to have to return a BigInteger on the way out because that's the return type of my program. Let's do the same thing down here. And the only reason I know it's BigInteger.1 is just by experience of having used BigInteger in the past. Let's suppose you'd like to actually go figure this stuff out on your own though. Before we dive into the actual implementation, I want to show you how you can get access to good documentation for how these stuff works. I'd like you, whenever looking for docs, to make sure you search for Java BigInteger 11. Specify the name of the class, and then specify the version of Java that we're using, which is 11. Forget about all these other links. Maybe Stack Overflow is useful. I really want you to focus on the Oracle link, which is, of course, the company that creates Java and the one company that updates these official documentations. Let's learn about BigInteger. BigInteger computes arbitrary precision integers. We get a longer description of what to expect. We get some static fields like 1, 10, 2, and 0 that are just static constants that can refer to 4 big integers that represent 1, 10, 2, and 0. We learn about the constructor. We learn about how to translate strings of big integers into big integers. And we learn about the different kinds of methods that are available to the big integer. Remember that I told you how we couldn't quite use those primitive operators for these object types. Instead, we get these nice functions that are attached to the big integer itself. So by nature of it being an integer, I would expect to see mathematical operations here, and I'm happy to see things like divide, equals, max, min, modulo, etc. So essentially what I'd like to do is convert my primitive ints and my primitive operators into these big integer method calls. Let's go back to our code and take a look. Let's replace these definitions with big integer equivalents. And rather than using the plus operator, let's go ahead and use the add method that's given to us from BigInteger to add two numbers together. Here we go. I can use the add method to take a big integer to return a big integer whose value are those two values combined. Okay, now let's get into the body of our for loop. Our for loop is a little bit more complicated because we're going to have to replace these definitions and these conditionals with big integer equivalents. But what you'll see is it's actually going to follow very much the same structure. Let's go ahead and initialize a big integer with a value of 2. I know from experience and from the documentation that I know BigInteger.2 exists. For this comparison though, I might be able to use the primitive operator, but let's avoid using it. Let's use a method instead. I need to be able to compare a big integer I to the big integer n that was being passed into my argument. When you compare two object types, that is, objects that are orderable, that have a natural order to them, you can use the compare2 method to determine whether or not a value matches another value and where it belongs in terms of ordering. Now, compare2 is a method that's actually native to a lot of objects inside Java. And we're going to talk about compare2 in depth in a later lecture. But what you need to know now is that compare2 is going to have to tell us in some way how the reference matches the argument. I know from experience that compare2 is going to return a number that's -1, 0, or 1. And -1 and 0 are going to indicate that I is less than n and I is equal to n, respectively. Whereas when compare2 is going to return 1, it's going to tell me that I needs to be greater than n. So what I can do here is use the output of compare2 and the number that it returns me to tell me that so long as I is less than or equal to n, I'm okay. I want to continue incrementing my value. Last but not least, the increment step. Well, I was told in this description of BigInteger that BigInteger itself is immutable. That means I can't directly change I, but instead I can replace I with I replaced by something with the I plus 1, right? And we know what the add function does. It gives me a big integer that combines two integers. So let's go ahead and use the add function there. Perfect. So now I've converted my for loop into a for loop that uses big integers rather than primitive integers. Let's go ahead and replace these last operator calls with big integer equivalents. Next is going to be first.add of second, and then I move my references forward such that first is the second, and second is the new next. Finally, I return next when I'm done. Okay, great. I've gone ahead and converted my Fibonacci to use big integers rather than primitive integers in the hopes that with unlimited precision, I'm not going to hit that integer overflow problem I was hitting. We're not quite done yet. I do have to replace some of these other things, these other type declarations, with big integer instead. So let's go ahead and do that. Let's make a big integer array. Let's make it take a big integer. We'll use BigInteger.0 here. We'll use compare to the up to index field to determine whether or not our number meets that index. Which reminds me, by the way, I should check down here to make sure I used less than or equal to, because I'd like to compute the nth value where I is equal to n. Here I like to reach the value that's up to index, so as long as it's negative, as long as I compare to up to index is -1, I'm happy. Let's replace this increment with I dot equal I dot add of big integer 1. And let's go ahead and store those computations. That's the same. Okay, one last thing. We got to replace this primitive int 5000 with a big integer. And unfortunately, we don't have something like big integer 5000. So instead, I can let you know from experience that big integer value of is how we convert a primitive type long or integer into a big integer. Okay, so I just wrote a whole bunch of code without very much IDE assistance. Let's go ahead and see if the Java compiler tells us if we have any problems. Oh no, we have some problems. I've got an illegal start of expression. Looks like I shouldn't have that semicolon in there, so that's definitely a problem. Let's go and try it again. Uh-oh, I can't convert a big integer into an array index. That's not okay, obviously. Let's go ahead and change this argument back to a primitive integer, because we're probably only trying to find some number that fits within the integer space in terms of n, where n is refers to the nth Fibonacci. Unfortunately, I have to go back in time, though, to undo all this heavy lifting. Let's go ahead and actually just revert within side VS Code to take us back for that particular block, so I can keep this integer argument, but end up returning a big integer on the way out. Big integer array, that is. That's going to let me keep this primitive for loop that uses the primitive arguments and operators rather than that big integer mess. Let's try it one more time. Okay, big integer cannot be converted to int. Makes sense. Let's go ahead and fix that. That should be 5000. And one more. Incompatible types. Int cannot be converted to big integer. Why is that? Well, fib of I, Fibonacci of I think it's referring to this I right here. Thankfully, there's that little caret there. Let's go ahead and make this big integer value of I. Let's run Java C. No warnings. Awesome. Now let's do Java for the moment of truth. Wow. Those are some pretty big numbers, huh? Man, I can hardly fit it inside my scroll window. I can't, actually. I physically can't fit it inside the history of my console. Let's try a smaller number so I can actually see what's going on. Let's try 100 to start. Don't forget to recompile. Okay, even at 100, let's see, it's kind of hard to scroll. I start out with my basic sequence, so I know it works correctly and my big integer is functioning. Then I keep going and going and going, and I get these massive, massive numbers. Fibonacci just grows so fast. Let's go ahead and do something crazy, like 10,000, twice as much as our last limit. Oops, forget to compile. it's going. And this last number is huge. I don't even see where it stops. There it is. Maybe it's this big number right here. Oh, there it is. In any case, I think you kind of know the point here, right? Is thanks to BigInteger, I can get around this integer overflow problem by having integers of unlimited precision. Unlimited precision in the sense that those integers are smart enough to grow in terms of bit width when I start to reach the limit of the integer itself. As you recall, the int is 4 bytes. I can only store numbers that are so large. The long is twice as precise, but I can still only store a finite set of numbers in there. The BigInteger is going to give us this abstraction of unlimited size ints. Abstraction, that word again. How does that apply here? Well, think about the implementation of BigInteger. The BigInteger has to know when I'm approaching a number that's too large for the size it currently stores. It has to know that it has to allocate more space to fit more numbers inside when I'm starting to reach the limit. And it has to do that repeatedly and totally abstractly to me, who is just using the API that is expressed by the BigInteger. What I mean by that is I don't think about how the BigInteger widens. I don't think about how the BigInteger grows and how it deals with overflow. All I care about is that I can call the add method, or the compare to method, or maybe the equals method. There are really only 3 methods that I'm using that are very basic methods to work with to be able to use this very, very powerful class. This is the great benefit of abstraction. I get this robust and very useful class from the Java Standard Library that was written by some very smart engineers, probably at Oracle, and I'm able to use what is probably a complicated class underneath that has to do a lot of bitwise operations with just 3 basic method calls that are very easy to understand and look up. That is abstraction in action. I've abstracted away that complexity of implementing the BigInteger just by getting this nice interface, these basic method calls. That means I can use the BigInteger without knowing at all how the BigInteger is implemented underneath. Okay, let's go ahead and commit this stuff because I like it. Let's go ahead and add Fibonacci. Let's do a git diff so we can review our changes. Change the number 5,000 to 10,000. Change our ints to BigIntegers. And down here, I changed all my primitive values into BigInteger values. Git status, git add Fibonacci, git commit m, replace int with BigInteger. Awesome. One more git command I'd like to show you, git log. When you do a git log, you can use the arrow keys to scroll up and down through time to see how you have been developing your program. Our first commit was implement recursive Fibonacci. Remember that very basic version of Fibonacci that took forever. Our next commit, we replaced it with iteration. We tried upping the value of 10 to 5,000. We hit the integer overflow. And finally, we replaced the primitive int with BigInteger. Being able to view your history gives you different kinds of landmarks throughout the development of your code that tell you how it's being worked on and how it's being changed. With version control, when other people make commits, you can look at Git Log to see what the changes they were making are. Let me show you something real special. If you copy out this commit hash, you can actually check out not just branches, but commit hashes as well. Here is my primitive int version again. All I've done is gone back in time 1 step to go look at that primitive int version of my Fibonacci implementation. And really all it takes is going back 1 commit. Here's a command that just gives me the last 2 commits. And I've just gone back to the previous. Sorry, this is actually the 2 commits before this one. But I went back to the previous commit that was at the head of my branch. Let's go back to the very front, check out iterative, git log -n3, 1 line. That's going to give me 3 commits in 1 line. And the commit that I essentially lost by going back in time was this commit, replacing the int with BigInteger. And I did that by checking out the commit that came before it. Okay, I hope this has demonstrated to you the value of using version control. Let's do one more thing. Let's go back to that master branch. Oh no, I've lost my iterative implementation. That's okay. Remember that version control lets me save everything. It's all right. Last step here is I'd like to do a git merge. And merge essentially unites two branches such that one branch absorbs all the commits added to the other branch. Let's say my iterative experiment worked out really well, and I'd like to make that my new master branch and bring in all those commits that I made it. What I can do there is merge that iterative branch into the current branch. And that's going to bring forwards all the commits that I had pushed to iterative, but had not pushed to master. And what we get now is an implementation of Fibonacci that is of the latest version that was on iterative and now in the master version of the branch. Of course, if I want to go back in time, I can do that Git log. I can go and check out those individual commits and get any of the previous versions of my repository that I see fit. Okay, that solves our Fibonacci problem. I really recommend you download this code, you try to compile it, you play around with it, maybe try to go through the same process that I just taught you so that you'll have familiarity with using version control on your projects. Let's finish this out by going back to the README. A couple of other pro tips before I let you go. The git ignore file is a file that you can use at the base of your repository to tell Git to ignore certain kinds of files. Commonly, you want to ignore compilation output, like these .class files that come out whenever you do a Java C. This is intended so that whoever is downloading your source code compiles it on their own machines rather than using the compiled version for your computer because it might not be compatible. There's also some other random files that your operating system might generate for you. Like I know Mac likes to generate this folder called ds store. That's really not relevant to your code. You can add that to your git ignore. Commit early, commit often. Branching is cheap. It really costs you very little to make commits and make branches. Really all it is the act of writing that command to do the commit or do the checkout. Doing these branches will really let you expand upon the kinds of little details that you might be considering implementing in different ways without ever risking whatever working copy of your code already exists. So commit early, commit often. It doesn't hurt. If anything, I've regretted not committing more early and more often because I'll end up with these really big diffs that are hard to digest. So I encourage you to do it very regularly and on a regular basis. And finally, that cool time traveling step, go ahead and check out different versions of your code as you see fit. So that's a lot about Git. And for some of you, you might be really enjoying all of this and you're excited to work on this new tool or to work with this new tool that really a lot of people use and I really, really strongly recommend. For some of you, this is a lot of complicated stuff that you really don't want to use in your life, and that's okay. The great thing about software engineering in modern times is that we have such a great variety of tools and workflows and different approaches that you can really adopt the software and tool sets that you see are most useful to you. So if you want to use Git, awesome. There are tutorials that I link on the syllabus, and I'll give you 5 bonus points for every project submission that has that hidden Git folder inside. So you get a benefit out of it, not just from the capacity of having version control, but also a practical class benefit as well. If you don't want to use Git, that is totally okay. You don't have to use it at all. You don't have to install any of this. You don't have to really learn any of these commands, and I'm not going to ask you about it on a test or a quiz. But again, I really, really highly recommend you learn this stuff, and a lot of people use it, and it's really, really awesome, and it's going to really benefit you for the rest of your academic and professional careers. Okay, that was a lot to digest. That's all I've got for today's lecture. Thank you for listening, and I'll see you next time.